Yes, hello everyone. This is Gennady.
Fedor.
We are at the airfield. You can probably guess what we're doing here. We're assembling our first airship, unmanned, but version 0.1. By the way, here it is. Right now it's in the assembly stage, filled with gas to about 70%, so that's why it still looks so delicate. Yes, but actually there's just one more gas cylinder left to fill, and then it will take on a completely smooth shape like this. Let me explain how it's built. Well, as you can see, it's tethered. It's tied by the nose. The airship is held down by a net because it's already filled with helium and is trying to float up. Basically, right here is the nose reinforcement. It's made up of 12 duralumin beams that join together on a common flange, and this fitting here. All of this will be covered by a special body shell. This mooring unit connects to the mooring mast, which you saw outside at the very beginning. We won't show it to you just yet. So the nose reinforcement is needed for it takes on the frontal resistance.
When it's moving?
Yes, when it's moving. The airship is designed for a speed of 80 kilometers per hour, and as I mentioned earlier, it turns out that the laws of physics say the following. With a large cross-section, the pressure is more or less even everywhere, but the tension on the fabric at a large cross-section is strong. The smaller the cross-section, the less the tension, so the pressure inside seems to be uniform, but that's how it is. And that's why a nose reinforcement is created. So here is the filling valve through which the helium is poured in. The helium is filled through this kind of assembly. It is connected. Opened.
Applied.
One cylinder at a time. The cylinders are outside, and it takes about 4 minutes to fill it up here. Right now, there are about 16 cylinders in it, and to give it a fully finished look, it needs just one more cylinder at most. So what else do we see here? We see a technical hose. Through it we filled the main volume of the envelope with air, simply pressurized it, checked its airtightness, and so on. By the way, over there below the soapy solution is already prepared. After installing all the components, valves, interrupters, there's even a pressure receiver over there. All of this gets coated with soapy water and checked again. Yes,
so to detect any leaks?
Naturally. So this particular element here is assembled a bit differently further on. It folds inward. You see there's a special pocket where the membrane is inserted, and everything becomes smooth here. This part won't be sticking out at all. And here you can see the grommets. The gondola is carefully laced through them with a regular and securely fastened cord. Someone over there was asking about the friction of the hard parts of the shell. Right here we can see the shell, then, as you can see, a special lining made of a different material, then another layer of fabric for the grommet, and only after that, inside here is the rigid element. So there are two reinforcing layers right before the shell itself. So if we move further along, we'll see this pressure sensor. First it's connected like this, then through another hose, basically to the computer, right now to a stationary one, and later to the onboard system. Basically there's still helium inside here, and this helium reaches the sensor, presses on it, and that's how we can see the pressure inside the shell. It's the same thing, as I said, only with a different hose. It will go to the onboard computer.
So we'll always know what the pressure is and be able to monitor everything.
Yes, the onboard computer needs this in order to, well, to control the pressure using the ballonet, for example, to turn the fan on or off. This is the wire from the temperature sensor, which is also located on the pressure receiver, but from there on a kind of rod at a distance, I don't remember, about 30-something centimeters away. It measures the temperature of the gas inside the envelope. That's it. A special platform comes here. It's also mounted on a rod, and this is where the test mini brain is installed. There are a bunch of different sensors there. Sensors that will measure speed, its position, acceleration. There's a GPS module and a GLONASS module. And I think we can go now and take a look from the side at how the pressure and the external appearance of the airship. The pressure is rising. Well, as you can see here, the pressure in the gas volume is increasing. This shell can be easily poured up to 250. Right now it's a bit higher, but in the end everything should even out. When the valves are adjusted, the valves will equalize the pressure. The valves have turned on. You can hear that the valves are venting the excess pressure from the ballonette.
So it's not helium being vented, but specifically air from the ballonette?
Yes, but if, by the way, you take a wide shot, you can actually see it.
Yeah, you can really see how taut it is.
So right here there's a special net that keeps it from taking off, because right now it's being helped to lift by 100 kilograms of thrust in the form of 100 cubic meters of helium. There are 140 kilograms of sand here around the perimeter.
Each heavy bag weighs 10 full kilograms, and they help keep the airship from taking off prematurely.
Overall, you can see the tail assembly here. It's guyed with these cables to a special element that absorbs the load. They are also reinforced with multi-layer strengthening under the envelope. This is where the servo motors are installed. The servo drive is mounted right here. Through these channels, electricity and control signals are sent to the servo drive, which then uses a lever to control the tail assembly. This is the element.
Well, maybe I picked up the wrong one, but the point...
But overall, yes.
The point is there.
There is tail reinforcement. Here there are 6 beams, there are 12. It's also necessary to provide rigidity to the tail, because the smaller the overall diameter, the less tension there is in the fabric, and the less durable the element itself becomes. And so a tail steering device is installed here, right onto this flange. There will be 2 propellers located here, each of which will be responsible for helping to control the airship, especially when it is operating at 0 speed. So if we're already near the ground and need to turn, either this one or that one is activated and the airship turns. This is the main cable duct, the large one. It runs all the way to the gondola. Here, there are optical fibers and power cables that deliver energy first to the thrusters, then to the tail reinforcement. What else haven't we mentioned? Over there is the lower landing gear strut and also the rear one. It is necessary so that during takeoff and landing, like an airplane, when we don't take off vertically, but with a bit of a run up or land with a bit of a run, we don't hit the ground with the tail assembly. For this, there is a special wheel. It will be braced with the same kind of metal cables at the base of the tail assembly. And it will also stand steadily, just like this tail assembly. What else should I talk about? You can see the ballonette from here.
Yes.
This seam that you see, this one here, that's the lower edge of the ballonette. The ballonette is basically like a big inflated blister filled with air inside the airship.
And way over there?
Let's go, I'll show you. Right here, there are special valves. If we open them, air will come out from there.
Okay, got it.
Yes. They release air specifically to equalize the pressure in the ballonette and the envelope. For example, if the ambient temperature rises, the gas expands and compresses the ballonette, so air is released from here, and this is the fan. Then when cold air blows in, the gas contracts. For example, if the airship loses its rigidity, these fans are used to inflate the ballonette and increase the pressure throughout the entire airship. This is a special filling hose for the ballonette. With the help of a blower, air is pumped in there. During ground tests, it also folds up and the membrane closes. And overall, this is exactly where the gondola itself begins. In this small spot, the controller for this fan will be installed. On the opposite side, symmetrically, there will be a second fan in the same way. A microcontroller will be placed on this membrane, which will control that controller. And that's it. After that, the gondola begins, and everything else will be installed inside the gondola. We can go over to it. I'll show you what will be located where. Basically, we've just started assembling the gondola. You've already seen it fully assembled in the office, how it was there. Then we took it apart. Now we're putting it back together.
It's not the first time already.
Yes, there will be one main engine here, another one over there, propellers, controllers. The wires come out from here and go in the onboard computer. The onboard computer is located right here. Here is a servo motor that controls this beam. We can change the rotation, well, adjust the thrust vector. So if we set it like this, we can add more thrust. There will be about 90 kilograms of thrust from the two engines at peak. Well, downward means it will be pressed back toward the ground, obviously. This way it will fly forward along its course. The battery will be located here, as you can see, and it will supply power to the computer, while the VGS system has a separate power supply. Here, most of the power will go to the batteries. Inside one case, there are actually two batteries. Power will be supplied to the main engines, the tail steering device, and the tail assembly. And a small amount of power will go to the mini brain that's mounted at the front, which will be located up front with the sensors. The interrupter will be located here, following the same scheme as the flight interrupter. Here there will be an aviation circuit breaker installed, which will also disconnect the main line at the push of a button if something goes wrong. This is the landing gear beam. For now it looks like this, but wheels will be attached to it here. Overall, in broad strokes, that's the entire gondola. The only thing is, there will be a bunch of wires and optics here, and the propellers. The propellers are three-bladed, the ones we've been waiting for.
We packed them very securely.
They're sealed with tape. Yes, so this is the tail thruster unit. There will be two propellers here. These are the motors, they're packed up. There will be a propeller here and a propeller here. Inside there are two controllers, a microcontroller. Power comes in here, power for the controller and power for the microcontroller and the optics. The microcontrollers come here, they will arrive here tomorrow. Here. This is what the main engines look like. Here they are marching. But on the Nova airship, two of them will be in the tail thruster.
Fedya, if we suddenly get caught in the rain in the next few days, will that somehow interfere with our ground tests?
Of course. We won't be testing anything at all in the rain for now.
We'll be waiting for good weather.
Yes, at first we need the weather to be as perfect as possible. No wind, no rain, nothing, because the craft is still unpredictable. It has a minimal number of automatic control systems, and it's mostly operated manually. Overall, an airship is much easier to control than, say, an airplane, a helicopter, or a quadcopter, because it has Archimedes' force lifting it up. Its entire weight pulls it down. There's a center of gravity, and the center of gravity is below the center of volume, so it's always balanced.
So it's at zero.
It can't flip over, it can't fall, nothing like that. But still, because the envelope is quite delicate, any unwanted contact with the ground, let's say any unforeseen contact, is undesirable. That's why initially it's safer and more reliable to fly in calm weather.
Did we have any issues perhaps getting permission for the flight tests?
No.
How did the administration react to the fact that we would be flying a dirigible here?
The administration was impressed. They were a bit frozen in anticipation of this flight.
It's just that I often see questions in the comments about how dirigibles will coordinate their flight tests with airfields. Yes, basically just like any other aircraft, whether it's a helicopter or an airplane. You contact the control tower and get permission as usual.
Yes, but for that you need a registration number. Ours is still being processed, so we can't register it yet. There are dedicated services for this, and there are actually two different procedures involved. If you are a scientific organization, that's one procedure. If you are a commercial organization, it's a different procedure. And now, most likely, it's time to set up our first subsidiary there, specifically with a scientific profile for this purpose. Plus, there are some extra perks. There are special testing grounds. If you are a scientific organization and you work on things like this, then access to the testing grounds is open to you.
Hi guys. When does the stage change happen, and what work needs to be done to move on to the next stage?
Listen, it would make sense if it happened after success, yes. But
we also have a financial goal that needs to be achieved as well.
Yes, we do. You need to clarify all this with Pavel Filipov, but logically it seems like it would be after successful tests, after the first flight.
Will all the sensors that are being tested on the Malesh be used on the larger airships as well?
On the Malesh, there's an experimental version that's loaded with sensors so we can collect certain data, and then roughly speaking, there will be commercial versions. You won't need as many of the interesting things that will be on this one. And the same thing will happen with the Nova 2. At first, it will be completely covered with sensors so that we can simply learn how to control it properly and understand how it behaves in certain situations. And then, yes, some of the sensors will be removed, more or less. Yes, of course, there will be more of them, because a proper gondola will be added there. And overall, it's a passenger version, so the requirements for it are completely different.
What does the company Aeronova need to do to surpass SpaceX in terms of valuation?
Well, look, when the 10-ton model flies, that's already going to cause quite a stir. Ideally, by then, the company should already be listed on some stock exchange so that someone can actually record its value, because otherwise all these valuations are just ephemeral. But when something like a 60-ton or a 100-ton model flies, that's when the company will really be worth something. I don't know, it's unlikely anyone will let it surpass Elon Musk. Besides, Elon Musk is planning to go to Mars, but we'll definitely be catching up to him, considering that he'll also be moving forward, so to speak. We can move at a steady pace, and even if we're behind, we'll be catching up to him. And what should we do? Just do our job, build airships. Here is our mooring mast, as you can see. Right now it's in a state as if it's ready to receive an airship for docking. The only thing is that the mooring head hasn't been raised up to its working position yet, but overall all the legs are firmly planted in the ground. All the guy wires are secured and the structure stands confidently. Ruslan put it together in his spare time. Overall, the structure is sturdy. I weigh 90 kilograms and it doesn't wobble.
The mooring head can be raised even higher.
Yes, it's on bearings, which allows the whole thing to weather vane. The cable here is just for looks. In reality, it fits in here with a special pin. The whole thing is anchored there, so the airship can weather vane and stay in place. You can also fold it up, hook it, and drag it somewhere farther away.
That's it, friends. Thank you all. Be sure to like, comment, and share. And
why do you always have to ask for likes?
We need any kind of activity, that's all. And now, in a very beautiful and epic way, we take off. Oh, careful, my friend.